Let's take a look at this. We are asked, first we're given with matrix A, whose entries are 1, 2, 3, 4, and matrix B, whose entries are 0, 1, 1, 2. We are asked to calculate for A plus B and B plus A, and determine if matrix addition is commutative. We're also asked to calculate for 8B and BA and ask if matrix multiplication is commutative. So pause the video and try to solve for A plus B, B plus A, AB, and BA. Alright, so let's first do A plus B. So if we're going to have A plus B, that will be this matrix plus this matrix. So therefore, we're going to have 1, 3, 4, 6. Let's see if B plus A will yield the same result. B plus A would be 0, 1, 1, 2 plus 1, 2, 3, 4. So 0 plus 1 is 1, 1 plus 2 is 3, 1 plus 3 is 4. Oops, we forgot to close that. And 2 plus 4 is 6. So we can see here that A plus B and B plus A would have a similar result. So it would be safe to say that matrix addition is commutative. We're actually going to explore these properties in the next lesson. Now, let's take a look at AB and BA. So for AB, we are going to have, oops, there you go, 1, 2, 3, 4 multiplied to 0, 1, 1, 2. So therefore, we're going to have the result of, after performing the operation, I'm not going to show in detail how it would happen. This one would become 2. And this one would end up with 5. This one would end up with 4. And the last entry would be 11. So this is the product A times B. Let's take a look now at the product B times A. So B times A would be 0, 1, 1, 2 multiplied by 1, 2, 3, 4. So I'm going to have here 0 times 1 plus 1 times 3. That's already 3. 0 times 2 plus 1 times 4 is already 4. Then the next entries would be 7 here and 10 at row 2, column 2. And here, as you can see, they are not the same matrix. They may be the same size, but not the same matrix. So this gives us a hint that matrix multiplication might not be commutative, unlike matrix addition. We are going to explore these possibilities once we look into the different properties of our operations. Now, one practical application of matrix multiplication is representing a system of linear equations. Now, the system can actually be thought of as the process when we multiply our coefficient matrix to our matrix of variables. Because if we're going to do this, if we're going to multiply this coefficient matrix to our matrix of variables, it will be as such. So let's go down with that. There you go. So if we're going to multiply these matrices, the coefficient matrix and the matrix with the variables, we're going to have A sub 1, 1 times X sub 1 plus A sub 1, 2 times X sub 2 plus A sub 1, 3 times X sub 3 will be equal to B sub 1. This is actually the first row. The second row will just be A sub 2, 1 X sub 2 plus A sub 2, A sub 2, 1 X sub 1. because that's how the matrix multiplication works. Then a sub 2 times x sub 2 plus a sub 2 3 times x sub 3. Then the other one, a sub 3 1 times x sub 1 plus a sub 3 2 times x sub 2 plus a sub 3 3 times x sub 3, which in turn will just make us go back to the original system. So we can represent a system of linear equations as actually a matrix equation ax times b, where A is the coefficient matrix of the system and x and b are column matrices. X are the column matrix of the variables, b are the column matrix of the constants. So, seeing it in this example, we are asked to solve the matrix equation A sub ax is equal to 0, where this is matrix A, matrix X, and matrix 0. So, applying what we've had seen a while ago, this is actually this system. Ax equals 0 is actually 1, negative 1, negative 2, 1. Oops, that's just positive 1. There you go. Then 2, 3, negative 2. Multiplied to x1, x sub 1, x sub 2, x sub 3 is equal to this matrix, which in turn is actually a representation of the system of linear equations x sub 1 minus 2x sub 2 plus x sub 3 equals 0, because we multiplied that, and then multiplying it again, I'm going to have 2x sub 1 plus 3x sub 2 minus 2x sub 3 equals 0. So now we have a homogeneous systems of two equations in three variables. So then we can now solve it as how we solve our systems of equation. So we're going to go back with rewriting. We already have this one here. We just need to include our this matrix rather for our augmented matrix. So our augmented matrix from this system would now be 1, negative 2, 1, 0, 2, 3, negative 2, 0. Now, since this is a homogeneous systems with three variables but two equations only, we expect that we're going to have infinitely many solutions. Now, performing Gauss-Jordan elimination, I'm now going to show the RREF. The actual process rather of the Gauss-Jordan elimination is left to the viewers. After performing Gauss-Jordan, we're going to have the following matrix. 1, 0, negative 1, 7, 0, 0, 1, 4, 7, 0. This would mean that I'm going to have the equation x sub 1 minus 1 over 7 x sub 3 equals 0, while here x sub 1 plus 4 over 7 x sub 3 equals 0. So therefore, the non-trivial solution of this system can be seen as x sub 3 equals t, where t is an element of the set of real numbers. X sub 1 is equal to 1 over 7t. This should be x sub 2. So x sub 2 will be equal to this should be negative 4 sevenths. So this should also be negative. That's why x sub 2 will be positive 4 over 7t. So this is one application of matrix multiplication. We're going to multiply these to create a system and solve the system of linear equations.